The last time we looked at an example of a reversible reaction. It's shown here above. And so what happens when this reaction, or any reaction where a forward and a reverse reaction exists, comes to an equilibrium, at that point all the concentrations of the reactants and the products are stable. That means they no longer change. So when the forward reaction is equal to the reverse reaction, we can measure the concentration of chloride, for example, and it will not change. And so that allows us to come up with an equilibrium expression. That means that ratio of the concentrations of the products divided by the ratio of the concentrations of the reactants is always constant, right? And so you can write an equilibrium expression. This is going to be K equals to the concentration of the products times the coefficient. There's no coefficient, that's just a charge, so that's a 1. Here you see that 4, so times the concentration of chloride, and so brackets means, just as a reminder, molarity or moles per liter. And then you divide by the concentrations of the products times their coefficients, so times this cobalt chloride complex and water, concentration of water to the 6th power. And so if you now shift, like we discussed with the Le Chatelier's principle, like if you are shifting this equilibrium now, let's say you add a source of chloride to it, and it shifts to the left. Once it reaches equilibrium again, this ratio then is again equal to the constant, and so that is very meaningful, and we can do a lot with that. And the magnitude of this equilibrium constant also tells you how far the reaction is going. If this is larger than 1, you have more products, and if it's smaller than 1, you have more reactants. And so the larger the equilibrium constant, the higher the amount of products, and that makes sense mathematically, right? If the concentration of the products is larger than the concentration of the reactants, you get a number that's K that's larger than 1. So the example from the beginning of the chapter is hemoglobin. That's a reversible, or the reaction with hemoglobin and oxygen is a reversible reaction shown here. Hemoglobin, of course, is a complex molecule that is responsible for oxygen transport oxygen transport from the lungs to the muscles through the blood. And so here abbreviated as HB, the reaction shown, hemoglobin binds oxygen and then reacts to form this HbO2, and this is what travels through your blood from the lungs to the muscles, and then oxygen also should be released, and so it works like Le Chatelier's principle does. In the lungs you have a high concentration of oxygen, which means the equilibrium is going to shift to the right, forming more of the bound hemoglobin, or the oxygen that's bound, right? And that's what you want. And then when you get to the muscle here, you want that to release. So when you are at the muscle, hemoglobin will then release oxygen, so it'll shift to the left and release oxygen in the muscles. Take that up. And so there's going to be some sort of equilibrium constant associated with that as well. And the magnitude is probably pretty small. But there's actually a difference between fetal hemoglobin and normal hemoglobin, and the equilibrium constant of the fetal, here abbreviated with HbF, is larger than that of the regular hemoglobin. And that makes sense because the babies, although they do have lungs, they don't breathe. There's no high concentration of oxygen. Therefore, you have to have more binding of oxygen in the hemoglobin for the fetus. Okay, so when we first start a reaction, this is another example. It's simpler. Again, we have here K, products HI squared divided by H2 over I. 2 has some sort of equilibrium constant. And it's also noteworthy that the constant will change with temperature. That makes sense. We looked at an exothermic reaction that can shift, and so it makes sense that if you're at a higher or lower temperature, you can alter the equilibrium constant. But it should be the same if you keep the temperature constant. So when you first start the reaction, as we've said here, that would be, this is kind of like a reaction coordinate. You start at time 0 when you are adding hydrogen gas and iodine gas together, or iodine, yeah, it's in the gaseous phase. You have high concentration of your reactants and you have no HI, and so initially you have a fast rate. The disappearance of hydrogen and iodine, you can see here it decreases, and then your product increases. But as you know, the minute the product is formed, you also have the reverse reaction, which decomposes it, and at some point the two rates are the same. That's what's shown here by the dashed line. So the rate of formation and the rate of decomposition are equal at that moment in time, and that's when you can see here the concentrations are leveled out and they are the same, and we can apply the equilibrium expression. And for some reactions that's very fast, and for other reactions that's a slow process. Okay, so here this is a pretty busy slide, but this is the same reaction, and it's all carried out and measured at 445 degrees Celsius, right? And so we have initial concentration, so we mix different concentrations of reactants, and then once it establishes equilibrium, we measure the concentrations of the products and the reactants, and we can calculate an equilibrium constant. So that's this formula here, and so we have these different measurements: 1, 2, 3, 4, 5 different experiments. You can see you start out with 0 and equal concentrations of HI. Then we allow it to react, and we measure the concentrations of the product and the reactants, plug it in, and we get an equilibrium constant of 50. And so here we have no reactants and we have only product, and then of course that shifts left, and once establishes equilibrium, we measure the concentrations of all of the present species, and again we end up with the same equilibrium constant. So these are just 5 different measurements mixing together different concentrations of reactants and products, and then allowing the reaction to proceed. So let's practice. This is really simple, how to write an equilibrium constant for a reaction that is at equilibrium here. So that's again that arrow. All you do is you write K equals the concentration, so you put this of the products times the coefficient, so here to the 4th power, divided by the concentration of the reactants, into 0.5 squared, and there's just one reactant, so that's equal to K. That's pretty simple. So we only are going to incorporate the concentrations of gases and aqueous species. So if we have, here's the solution. If we have solids and liquids, they have a constant concentration throughout the reaction, so we ignore them here, right? So if you have a calcium sulfate, a calcium carbonate that's decomposing, which produces carbon dioxide, and calcium oxide, the only thing that matters to the equilibrium constant is the gaseous species here. The solids don't matter. So K is going to be equal to the concentration of CO2 and not calcium oxide, and you are done. That's the equilibrium expression. The same is true for liquids, for true liquids here, right? So you're forming water when you react hydrochloric acid and oxygen gas. So this will also not show up in the equilibrium equation. So we have chlorine to the 2nd power divided by hydrochloric acid concentration of times O2 to the first power. And again, the liquid does not show up. So remember that if I ask you to set up an equilibrium expression. Here's a clean slide for that. We can take two different reactions that are reversible, and we can determine the equilibrium constant if the reaction is related. It's very similar to thermochemistry, right? If you have a reaction like this here, nitrogen-hydrogen gas, that happens to be it's called the Haber-Bosch process. It's a pretty important process. The formation of ammonia, which is used to make fertilizers. And so this K here, it's got a very large K, which is good if you want to produce a lot of ammonia. And if you simply reverse that reaction, okay, so this is actually an endothermic reaction, so it would have a delta H value of positive. Oh gosh, I just want to give it a number. So let's say 100. I made that up, obviously. And so if you reverse that reaction and you kept the coefficients the same, then the delta H of the reverse reaction, you can see here, would be the delta H would be negative 100, simply because you're reversing it, and you're also dividing this reaction by 2 here, if you remember. So instead of having 2 moles of ammonia and 3 moles of hydrogen, we have half of that. Then we would also divide this by 2 if we were to do this with thermochemistry. I'm hoping you remember that. We can do the same thing with equilibrium constants here, right? So the equilibrium constant of the reverse reaction would simply, so K prime here, would simply be 1 over 5.6 times 10 to the 5, but also to the half power, okay? So if I was to reverse this reaction here, just to elaborate just a little bit. So we have 2 NH3 going to 3H2 and N2. Then the K for that would be 1 over 5.6 times 10 to the 5. Now if I set up an equilibrium constant for that, it would be H2 to the third power and N2 divided by NH3 to the second power, okay? And the equilibrium constant for this reaction would be H2 to the 3/2 times N2 to the 1/2 all over NH3, which that is the square root of that, right? That would be equal to K prime. So this is where that calculation comes in. Let's step things up a little bit. You can also look at chemical reactions and combine them to come up with a new equilibrium constant, as long as all of the reactants and products add up and those intermediates cancel out. That's exactly how we did it for thermochemistry too. We had a delta H of one reaction, so if we had a delta H for this reaction and a delta H for that one, we could combine these two reactions to come up with the enthalpy of formation or for the reaction for this process. So we can do the same thing for K here. You just need to look at the two reactions and then make sure they're in the right order. And so if you look at this one here, it has water as a reactant, but we want water as a product, so you need to reverse that reaction. So that's the first step we're going to do. We're just simply going to reverse that. So we have CO2 and H2 forming CO and H2O. So that's just reversed, and so the K for that would then be 1 over K2. And now we are simply going to add these two reactions together, the one that I reversed and the one for the K3, so reaction 2 and 3. And so we end up with CO2 and CO. And then we have H2, 1 and 3 and 2 H2s, which together makes 3 H2 molecules. And our products are methanol, CH3OH, and carbon monoxide, and then that should be in the gaseous phase, and then 1 water. The CO here, we have one on the reactant part and one on the product part, and when you look at that reaction, it is actually equal to the one that's written here. That means the K for that reaction is K3 divided by K2. Alright, so here's the, it's all worked out nicely. Yeah, I should have probably written that out, but you can do it mathematically. I won't do it now. But you can set up the case, and you can then also figure out what the equilibrium constant is. Okay, that's enough. I'll see you when you're ready for the next lecture.